bam. So the early portion of the class was just me, talking about other stuff. So here we are. That's a shame. I thought I had some funny remarks that were, forever recorded on the cloud, but denied. That's what it sounds like. Folks, so I encourage you now to check in with your friend as to, even if you haven't gotten to the final answer, how are you going about it? And again, my hint was to check the previous example, which was this one right here. So I think if you check that one, and we had a solution for that one, h1 over 1 plus h1, h2. It might help you out with this one right here. Okay. And if you're at home and you feel you've got a pretty good idea, feel free to chat or type into the chat what your answer is to this one. Okay, so I see one answer coming in via the chat. So Hunter is telling me in my numerator, I got K times G1, G2. In my denominator, I've got 1 plus K G1, G2 times H, and H is showing up in multiple places. So I'll say, Hunter, you are almost right. You're almost right. That's a very dire reaction, but there's a lot to feel good about there. So let's.
I had it.
What's that?
I thought I had it. I was so confident.
Oh man, yeah, no, it's. I appreciate the honesty. That's refreshing. So, is there anyone here that can tell me how to tweak Hunter's answer, or if you're somewhere close to what he's getting? Okay, so at least in the class, no one has figured out your error, Hunter, but let's review it together. So over here in our previous example, the one that I told you to compare it to, we have something in my, so we've got a feedback system. Essentially, you got your input signal here, output signal here. You've got a main sort of like direct path, and then this thing that's feeding back. And we've got H1 in my sort of like direct path, H2 in my feedback path. And so we said if we have a situation like this, it's going to be H1 over 1 plus H1, H2. So the direct path here, and then 1 plus direct path times feedback path. So we can use that same concept over here. So if we look at stuff that we've done in previous examples, we know that if we've got several in a row, we can just multiply them together. So here I've got my K, G1, G2. I can just treat that as one thing. So call this K, G1, G2 right there. And then I've got H in the bottom. So I'm gonna draw it below with that simplification. Basically, I would have this thing, combining it all into one. Oops, and then X as my input and Y as my output. Okay. So that's making the simplification of combining the 3 blocks along the main path into one. Now, if we compare this one to the previous example, we'll see they are almost identical. So if I, again, look at this thing up here, I've got something in my feed or my direct path, one in my feedback path. Same here, I've got 1 block in this one and 1 block coming back. So I can use the exact same structure and say, well, my Y over X is going to be equal to, it was direct path over 1 plus the product of the 2 of them. So in my direct path, I've got this guy, KG1, G2, over 1 plus KG1, G2H. And so that right there is going to give you the ratio of, that's going to give you the ratio of Y over X, which is your transfer function. Okay. So yeah, I think Hunter, you can see you were almost there. Yeah, but the H just shows up the one time. Doesn't need to show up all 3 times. Great. You could have, if you didn't remember the similarity to the previous structure, you could have also done it from scratch and written out what's this intermediate signal. Let's call it E. Let's call this intermediate signal right here M. And you could have set up your equations and said, you know what, you could have set up equations. I'm not going to go into it like fully in depth, but you could have set it up this way: Y equals here K times G1 G2E, and then said but E is X minus M. And then plug this into there. So Y equals K G1 G2 X minus M. And then said, but this M, we can get rid of it because M is going to be H times Y. So you would have said Y equals K G1 G2 X minus HY. And from there, after a little bit of algebra, you would have come to the exact same conclusion. From there, you would have gotten there. Okay. But it's much faster if you recognize topology that you already had worked with before. So that's what I'd encourage you to do. Great. So that's a little bit of practice there with this combining different blocks. Now, again, you'll get more practice with that in the homework, and it'll keep coming up in this course. So if you feel comfortable with this, with the summation, with the multiplication, with this feedback structure, I mean, that'll all come in handy. And just know if you get some weird structure that you're not very familiar with, you can always use this strategy of pointing out those intermediate signals. And by pointing out those intermediate signals and writing the equations, you'll be in good shape. All right. So any questions with this example here? Anything about this one that was confusing or yeah, just or that you'd like me to review? Okay. So something you might still be asking yourself is like, okay, now we know how to combine blocks. And we said that instead of having this h of t that we would have before for each system, we had these transfer functions in terms of s. So you might be wondering a few things. I mean, one, how does this relate? How do the G1 of S, G2 of S, H of S, how does that all relate to my time domain stuff on the one hand? And how do we, what does this even look like? What does a typical G1 of S, G2 of S look like? And is it going to be useful for something or other beyond just, combining them? What do I do when I combine them? So let's explore that in a little bit of depth. All right. So let's look at transfer functions and what they typically look like, what we can usually, I guess, conclude from looking at a transfer function. So again, typically, let's call it transfer function for this one. Let's call it h of s equals y over s, y of s over x of s. Okay. So again, this is going to be the transfer function of a system. Notice this is going to be the output in that frequency domain. Output in frequency domain. And right here, my x of s is input in frequency domain. And again, beyond that ability to combine those subsystems so nicely, it's pretty nice that we just got this nice ratio, output over input. We're just talking about frequency here as our variable. And don't forget, this is with initial conditions equal 0. Initial conditions equal 0. Okay. So while I will return to this in a little bit, you're like, oh, y of s over x of s, but what are those things? So y of s is going to be the Laplace transform of y of t. So this fancy L is Laplace transform. And I'll write in more detail like how to do that. And similarly, like x of s actually, usually we start with x of s, not with y, but x of s is going to be the Laplace transform of x of t. Okay. And while this is a little bit of review, I mentioned the process. If we want to find this y of t, so I'll say if we want to find y of t, which is usually what we want to find that output in time. What we do is we take x of t, we Laplace it to find x of s, then we run it through the system, so through that transfer function to find y of s, and then we do that inverse Laplace to find the y of t. So that's going to be our general strategy for this chapter and for the next couple of chapters. So we're bringing things from time to frequency back to time. And so we will explore a little bit of how this happens, both the part of bringing it to frequency. So all this is in the frequency world and the frequency domain, but then we're bringing it back to time.
Dr. Schrader,
Yes.
sorry, can you move the feedback a little bit? Thank you.
Yeah. So yeah, so again, Laplace is going to be that technique from which we move from one world to another. Now, when we are like this system, this H of S might be the combination of a bunch of different subsystems. So it might just be like the whole KG1 plus G2, all that stuff might show up here as your transfer function. Now, I'll say the typical look for what you'll see for I'll say a typical transfer function. Typical transfer function is, again, let's call it H of S. It's going to be a ratio of two polynomials. So it's going to be a polynomial in S over another polynomial in S. Okay, so we're going to have a ratio in polynomials, and let's call this P of S over Q of S. Okay. So typically, yeah, that's how we're going to see it. It's going to be a fraction, polynomial on the top, polynomial on the bottom. Now, this polynomial Q of S, let's say it's of order big N. This one is going to be of order big M. And kind of like we did in chapter 2, I'll say for, let's say a proper system, and this is something that's causal, something that's realizable in practice. So a proper engineering system, M needs to be less or equal to N. And the order of the system, when you hear the word, not just order of the polynomial, but order of a system is going to be equal to N, which is going to be the one for the denominator. So the denominator is going to be driving things for us. Yes, Dan.
Could you go back just to the system?
Could I scroll up?
Yeah, just for a second.
Yeah. Okay. Okay. So again, notice that typically you're going to have this ratio, and some of this stuff might seem reminiscent of the stuff from chapter 2, again, where we had M and N, we even used that Q of lambda, right? So when we were looking at the denominator, the characteristic polynomial, so you can see there's probably going to be a close relationship between that P and Q and the stuff from chapter 2. So there's one other like little bit of terminology here that's pretty useful. So there's something known as the poles of the system. The poles of the system. And these are the values of S. I'll say such that the denominator equals 0. So it would be such that Q of S equals 0. Poles of the system, which we're going to see in a sec, are super important for many things, but in particular for determining whether a system is stable or not. So value of S such that Q of S equals 0. And then we've got another related term, the zeros of the system. Zeros of the system are also going to be values of S such that, in this case, such that the numerator equals 0. All right. So we get there. So it turns out that the poles of the system are, again, they're super important. Poles of system, let's say, are essential to system behavior. So poles of the system are essential to system behavior. In particular, as we're going to see, they're the ones that determine stability. So if, so for example, if we want to explore Bibo stability, you guys recall that meant that as long as I had a bounded input, could I guarantee my output was going to be bounded as well? It was bounded input, bounded output. So Bibo stability meant my system was not going to blow up. It meant it was a system I could actually use. So it was super important to determine whether something was stable or not. Based on what we've had to do so far, it hasn't always been obvious how to figure out stability. We've had to go fairly in depth and say, well, let's assume that this one is bounded by M. Can I guarantee the other one? So it's a lot easier to do if you have a transfer function. So Bibo stability, I'll say basically what we're going to do is we're going to consider the poles of the transfer function. Let's say of V2S. Consider the poles of V2S. And you're going to have several situations. Basically, if let's say if all poles say have negative real part, then the system is Bibo stable. Okay, all poles have negative real part, systems Bibo stable. So a more elegant way to write that is basically let's say that let's call PI are the poles of the system. So let's call them P sub I. So if I say that the real part of P sub I is less than 0, then we can guarantee system is Bibo stable. Yet another way to look at it. So again, like the first way we wrote it was kind of in words. Poles need to have negative real part. Here we wrote it mathematically. We can also show it graphically. So if we do a little graph like this, okay, we do a little graph, and we're going to mark with X's the poles of the system. And you can think of this as having the real part right here. So real part, we're talking about frequency S. We're talking about values of S. So real part of S right here, imaginary part of S up here. And typically this is known as the S plane. So basically we want everything to have negative real part. That means it's going to be on the left-hand side. So as long as if you've got a pole right here, an X right here, that's great. If you got maybe, another one right there and right there, that's great. So all of this, like a system like this, as long as everything's on the left, then we're going to be in good shape regarding stability. So another way to visualize it then graphically is all poles are in the let's say in the left half, plane. Or LHP. So all poles in left half plane. Okay. So as a reminder, the poles are what makes the denominator equal 0. So you take that transfer function, you look at the denominator, set that denominator equals 0, you find those values of S, and you confirm are they all negative in terms of their real part, are they all on the left-hand side? Okay, so that's one good way to start with stability. Continuing on, if let's say, if you have at least one pole is on the right side, so if at least one pole is in this case the right side or the right half plane, then system is unstable. Okay. Which kind of makes sense. So even if you have, I don't know, if you've got 10 poles on the left and one on the right, that one is going to be enough to cause things to blow up. So at least one is enough to ruin things for you. So watch out for that. And then I'll say if there's poles right on the axis, so let's say if there are poles right on that vertical, on that imaginary axis, so on the imaginary axis, then we have a couple of different situations. I'll say as long as they don't repeat, system is marginally stable. System is marginally stable. So this would be a situation like this. If you've got your real part here, horizontal, you got your vertical imaginary part, and you've got maybe something like this and something like this. So maybe you've got S equal, I don't know, 3J and S equal minus 3J. And you're going to see, usually these guys come in pairs right here. So usually you've got one at the top, one at the bottom. But regardless, if you just have that and they're not repeating, then this would be marginally stable. Okay. Marginally stable. Okay, now basically you can think of marginally stable as being almost unstable, like on the verge of blowing up, or like if you tweak it just a little bit, it'll blow up, but you're not quite there. So your things are, they're okay, but they're extremely, extremely dangerous. So this is, you know, again, not quite blowing up for you. If you went a little bit over, then they would. But for now, it's still under control, just dangerously so. And I'll say, unfortunately, if there are repeats, then system is unstable. There are repeats, system is unstable. So if you had, instead of just this X right here, if you had like a double one right there, that would make the system unstable. All right, so this is stability based on transfer functions, and I mean I think it's much easier to identify, much easier to work with than stability. That's how we had done it in time domain. So let's just do a few examples so you guys get comfortable with this stuff. So an example right here. Let's say we've got this little block diagram. Okay. And let's say K is a constant up here. And then here, let's call this H1 of S. And here we have Y. So it's fairly simple little block diagram. And I'll say where H1 of S is equal to 2 over S squared plus, let's say, 7S plus 10. So just all I want you to do is determine is the overall system Vivo stable. Okay, so try that out. And you know what, kind of tied to that, I'll ask you to sketch location of poles and any zeros. There might not be any here, but poles and zeros. So whether you're finished or not, do check in with a friend if you're here in the class as to at least to stability. Did you come to a good conclusion there? Okay. So I see these gentlemen here are giving each other a thumbs up, which I hope means that the system is stable, or maybe you're just saying hello. Either way, it's a good thing. So the system indeed is going to be stable. So what we would do is we look at this denominator right here. So Q of S equals S squared plus 7S plus 10. From there, my poles, I would factor that out and make that equal to 0. So I would make that equal to 0. And for there, I get P1 and P2. And what did you get? -5, -2, I would guess for that one. Great. -5, -2. Because they're both negative, I mean, or at least their real part is negative, then we can guarantee that the system is going to be stable. So, so we know that real part of the poles is negative, so system is stable. Good. And then we said we can plot the location. So, nothing fancy here. We would put a real part on my horizontal, imaginary part in my vertical. And then I'm going to just put them right here, -2 and -5. And I would mark them with X's. So we can see that everything is on the left. Mhm. Sure. So as you can see, the poles are all on the left-hand side, which indeed makes, we can guarantee system's going to be stable. There's no zeros for this system. For there to be a 0, we would have to have S's and stuff in the top so that we can figure out an S that will make it 0. Here we just have this 2 there, so there's no zeros. So again, the X's represent the poles. Typically the zeros we draw with circles. In the system, but here there's no zeros to speak of. It's just the 2 poles. They're both on the left side, so the system is going to be nice and stable. All right, so that's a nice little warm-up one. Nothing too bad. Let's try this slightly more involved one here. So we've got this system here with X coming in on the left. And we're doing that little feedback structure. With nothing on the feedback loop. So on the feedback loop, we're just multiplying by 1 is one way you can think of it. But we have nothing there. And what I'll ask you is, so K is a constant. K is a constant. And maybe, or think of it like a constant, but like an adjustable constant. So it might be a dial that you can adjust. So K is an adjustable constant. So like a little amplifier that you can turn up or down. And I'll ask you for which values of K is the system Bevo stable. folks, I'll put you in little breakout rooms here so you can compare your answers. So. Okay, and I didn't send a breakout room invitation to you guys because you can just check with whoever's nearby. Since regardless of where you're at, do turn to your friend now and just check in and see, okay, what have we done so far? Do we agree on whatever steps we have done? So.
Yeah.
Yes, sir.
So when we were talking about those capabilities on the previous page,
Mhm.
do you remember when we had that, like the three actions and two of them were above and below?
Mhm.
What would cause them to be that way?
That's when you have imaginary numbers. So far we've had only real numbers, so that would be right on the axis. But if you've got an imaginary component as well, that'll drive it up and down.
Thank you.
Sure. Okay, I'll close these out. Okay, folks, so we're all back. Let's see, do we have anyone in the classroom that wants to volunteer an answer for that range of K that y'all got? No, everyone's too silent or too bashful. Folks, so give me something via the chat. And even if you're here, you can type in the chat if you're like, you know what, I think I have something, but I'm too shy to talk. You know, it's fine. So feel free to type it. Yeah, if you didn't quite get to an answer, we can still go over it together. Chase tells me stable if S is less than 0. Okay, so let's see, from Andrew I have, so solving the transfer function using a quick formula gives in class. That would be a good strategy. Julie is telling me K equals S minus 2. Okay, I feel like we're on the right track here. We're on the right track, folks. Yeah, and then Andrew's telling me I can simplify. Very nice. All right, so I think y'all are on the right track, but let's go over it together. So we said this was our system right here. Okay, let's see what else I have in the chat. Rand tells me K equals 2 minus S. So again, so we're on the right track. We want to make sure, like the question that we're trying to address is, so which values of K are going to make the system stable? Okay, which values of K are going to make the system stable? And again, it's a constant, so we can turn it up, turn it down. And for some it's going to be stable, for some it might not. So our first step is, as Andrew was suggesting, we want to use the simplification of this feedback system right here. So you can think of it as something that has a direct path and a feedback path. And you're like, oh, but we have no block here. So when you have no block, you're basically multiplying by 1. So instead of having an H2 or whatever here, you would have just multiply that by 1. And so when you do that, you're going to get that Y over X is going to be this block, K over S plus 2, over 1 plus the same thing, over 1 plus K S minus 2. So that's important. I hope y'all see like where this is coming from. And this is just, you know, applying something we already knew with our direct transfer function being this, and our feedback transfer function being just a 1 right here. So you got k over s minus 2, 1 plus k over s minus 2. So over here, we can do a little bit of algebra. So down in my denominator, I can simplify that s minus 2. So I get k over s minus 2 plus k by doing a common denominator. And notice that then I can just cancel this stuff out. And I get for my transfer function, y over x, I get k s minus 2 plus k. Okay, so far so good. All right, so I think it seems like a few of you have done there, and we want to make sure, like we're asking ourselves, okay, what is going to make basically this becomes our Q of S right here. And so we want then, we get this, Q of S is S minus 2 plus K. And we're going to set this equal to 0 in a bit. We're going to set it equal to 0. We're going to see for which values of S is this equal 0. Okay, so Q of S is that. Or I'm going to rewrite it this way, S minus quantity 2 minus K. Okay. So why did I write it that way? Basically, you can think of this as your pole, you know, PI. Okay. So if I set this Q of S equals 0, then I have it in the form S minus PI equals 0, right? And so we're asking ourselves, what value of S makes it equal 0? It's going to be PI. So again, this thing right here is my, yeah, this guy P1, I guess I could call it P1. But basically, this is my pole. I want to make sure my pole is on the left-hand side, so I do this less than 0. So from there, just moving the K over to the right, I get 2 is going to be less than K, or K greater than 2. Okay. So K greater than 2, this would be the range. This is the range of K. For stability. Okay. All righty, folks. So questions with this one? Notice there was quite a few things that we brought together. So we integrated how to simplify our block diagram on the one hand. So we had to find that overall transfer function, that y over x. Does it include or exclude the 2? So it's going to exclude it. If we had it equal to 2, then we would have that marginal stability case. So if you want it to be fully Bibo stable, you want greater than. Exactly right. So yeah, so if you have greater or equal, then that's like, okay, we're including marginal stability. All righty. So yeah, and so then we did a little bit of algebra, but then it was important here that it's like, okay, we have to look at the denominator, set the denominator equals 0, and then look at it from that point of view of S minus whatever, S minus a pole. And that S minus something, that is what needs to be less than 0. So that's our process. Are you guys feeling good about that? Should we do another example? Should we move on to another topic? No strong feelings. Okay, so, well, if you don't have strong feelings about that, I mean, you'll get more practice at home. So let's do a new topic. I mean, it's related to all this stuff. So basically, how do we go from x of t to x of s? We saw at the moment that we're in x of s, everything's great in the sense of we can easily figure out stability, we can combine blocks, we can do all this great stuff. So So it's a natural question. Okay, so how do we bring ourselves from being in time to being in frequency? And I guess I mentioned at the outset, the technique that we were going to use is Laplace transform. And there's a formula that we're going to use for Laplace, and it's this right here. So big X of S is this integral from 0, and we'll include the 0. So let's do 0 minus x of t e to the minus st dt. Excuse me. Right. So in your math class, you may have seen this go from minus infinity to infinity if you saw this in differential equations. So we're doing from 0 to infinity because in engineering systems, we typically work with causal signals and systems. So this one, I'll say this is used for causal signals and systems. If they were non-causal, again, you would use minus infinity to infinity. But this simplifies the math a little bit and actually simplifies it more than you'd think. When you've got the minus infinity to infinity and you try to compute that, sometimes things get a little bit messy. So this is a good thing, nice simplification. This is known as the unilateral Laplace because you're only going on one side, you're only going on the right. The one that you typically see in diffie-q is bilateral, but you got both sides. So it's it's an integral. We can build some basic Laplace transforms with just using this integral, but we can also, as we did with convolution, we can set up Laplace tables and use those whenever we can. So it's going to be a lot faster once we've got our tables, but just for good measure, let's do a few examples. So let's find the Laplace transform of a few basic signals. And how about, let's start with this one. Let's do x of t equal delta t. And I should write the nomenclature. So like how we write this thing of Laplace transform. So I'll scroll up right here. We say that x of s is fancy L of x of t. Calligraphic L. I've always found this to be a very visually pleasing equation. Just with a fancy L, the fancy little, these guys have a name, the fancy brackets? Curly brackets, that's the technical term. Yeah, sounds like curly fries or something, but yeah. And you got the nice symmetry here, the big old X and the little fancy, so I don't know, I think it's a pretty one. But let's apply it right here. Let's find if x of t is our delta t, our good old, this was our Dirac or delta or impulse. So let's find L of delta t. And you can use the above formula. So I'll give you a few minutes to try it out.
Curly brackets.
They are?
Yeah, or more colloquially, you could call them squiggly brackets.
Wow. Yeah, squiggly seems like a little bit of an overstatement. I mean, I see that, to me, that says curl, it doesn't say squiggle.
Yeah.
Yeah.
Just to give you at least one that's like,
Exactly, exactly. Yeah. There's got to be a more, like, we should come up with a more technical term. You know? Okay, great. That's a little bit unfair that was curly bracket and the square bracket is just called bracket, just by default, you know, like it's, you know, just giving way too much preference to the square one.
I've heard them called braces.
Braces, yes. I've heard that too. I think that's what I was looking for.
Yeah, braces is another name for them.
Okay.
They call them flower brackets in India.
Flower brackets, that's beautiful. I mean, yeah, that's fantastic. All right, so folks, let's check back in. So with, you've got the calligraphic L, you got your braces, curly, squiggly, or flower brackets around your delta. Man, yeah, I can build a nice thesaurus for all these things. And then we would set up our little integral right there, integral 0 minus to positive infinity. X of t is just going to be equal to delta t right here. And then e to the minus st dt. Okay. So hopefully this reminds you of the stuff back from the first exam, right? When you've got a delta and an integral. When you've got a delta and an integral, it's really nice because all you have to do is take whatever else is there and evaluate it, in this case, at t equals 0. So this is going to be simply take this and evaluate at t equals 0. So e to the minus s times 0, which is e to the 0 is equal to 1. So a nice little quick example. Basically, yeah, so we can say that the Laplace transform of delta t equal to 1. Now, another nice, I guess, type of nomenclature or symbols that we use when talking about time and frequency, we sometimes do this where you have x of t on the left, and then we've got this arrow back and forth, and x of s on the right. So that's another typical way we can express signals in time. So again, time domain here on the left. And then you got a dual relationship and then the frequency domain or Laplace on the right. And so one way we could write this is to say, well, then my delta t corresponds, or like in frequency, is equal to 1. All right.
Can you scroll up this to the, yeah.
Okay. Great.
Okay.
Sure thing. All right, folks. So let me just, while we're almost out of time, I'll get you thinking about this one. And this one you can do at home pretty quick. And we can start out the next class with this one right here. Well, what if x of t is equal to u of t? So as a reminder, this was our good old unit step. So all those nice signals from back in our earlier chapters that we're so fond of, hopefully we're fond of them. I'm very fond of them. We're revisiting now in the frequency domain. So we want to see what they look at in the frequency domain. Okay, so I'll leave this right here because it's 10:41. I think we moved a little slowly today, but it's, you know, it's a slow part of the semester. So as a reminder, we don't have class on Tuesday. Supposedly it's a professional development day for faculty. I don't know what they're going to have us do, I think it's one of those workshops similar to what you guys had with like diversity, inclusion, and things of that nature, I believe, maybe not. But I guess I'll find out on Tuesday. In the meantime, it's a little break for y'all. So I'll see you, well, in class, it's gonna be a while, but otherwise, yeah, I'll see you on Thursday.